All right, moving on to 10.4, we're now talking about polar equations. So a rectangular coordinate system is only one way to navigate through a Euclidean plane. Such a coordinate xy known as rectangular coordinates are useful for expression functions of y in terms of x. However, curves that are not functions are often more easily expressed in an alternative coordinate system called the polar coordinates. Okay, so if we think about rectangular coordinates, we think of this going through this rectangle motion where we move to the right and then we move up, or there's a horizontal movement and there's a vertical movement. In the polar coordinate system, we still have these traditional x and y axes. The intersection of these axes, the old origin, is now called the pole. Okay, so another word for origin is now pole. Similar to navigating on the unit circle, we can now get to any point in two-dimensional space by specifying an independent choice of an angle, theta, from the initial ray, the polar axis, and then walking out along that terminal ray a specified amount, r, radius in either direction. Okay, so with the polar coordinate system, we first start off standing at the pole, or this polar axis, this x-axis, and then we face in the direction that is facing this first quadrant. Okay, so we face the positive x-axis, and then we rotate some angle that will point us in the right direction, and then we walk along the concentric circles along this ray, a number of steps along these concentric circles. Okay, so let's see. All of the angle is the independent variable. We express the point in the polar plane as r theta. So this is a little bit different because we're used to seeing the first value as the independent variable. In this case, theta is the independent variable, but it's written as the second value after the dependent variable radius. Okay, so let's practice, or let's look at an example here. A point that we can graph right now is 4 and pi over 4. So pi over 4 is our theta, is our degree measure. So what we're going to do is we're going to find our angle of measurement from the polar axis, angle pi over 4, and then from there, once we find that, we're going to walk 4 units out along that terminal ray. So from here, pi over 4, 45 degrees, will take us to this terminal ray. And then this 4 means that we're going to walk out 4 units. So 1, 2, 3, 4. So this point will represent 4 pi over 4. Okay. Now, if this were the rectangular coordinate system, there would only be one representative of that point, right? Maybe this point, if it was a xy coordinate plane, it would be 3, 4. However, we can represent polar coordinates in multiple different ways, and still get to the same point. Okay. So for example 1, let's see. Before we do that, let's talk about actually the conversion. We can talk about after we get to example 1. So it says find several of other equivalent polar coordinates for the point shown. Then find the equivalent rectangular coordinate. So and we're going to just find the other equivalent polar coordinates within one rotation from the polar axis. So there are multiple ways that we can get to that point represented by 4 pi over 4. Okay, one way that we can do it is we can walk along in the direction of -4 along 5 pi over 4. So 5 pi over 4 would be from here all the way to the third quadrant, 5 pi over 4. But then if we're along this line, and if we're starting at the pole and going negative in the 4 in the negative direction, -1, -2, -3, -4, that will take us to 4 pi over 4. Another option is to go out negative 7 pi over 4. So negative 7 pi over 4 will be starting here, going in the negative direction to this terminal ray, and then walking out in the positive 4 direction, 1, 2, 3, 4. So there are multiple ways to represent the same angle. And then we can move either in the positive direction or in the negative direction. So the last one is negative 3 pi over 4. So negative 3 pi over 4. We start here. We go pi over 2 and then negative 3 pi over 4. And then we can, from here, we can walk, go out 4 units in the opposite direction. So negative 1, negative 2, negative 3, negative 4. So these are all equivalent polar coordinates that are within one rotation from the polar axis. Now, if we want to convert this to rectangular coordinates, these polar to rectangular coordinates, let's think about a right triangle. Okay, with the angle measure theta, the horizontal length x, the vertical length y, and the hypotenuse being r, or radius. If I write these trig ratios here, sine of theta will be opposite over hypotenuse, so sine of theta is y over r. Cosine of theta would be adjacent over hypotenuse, so x over r. And if I want to solve for r, I can make this, or if I want to solve for x and y, rather, if I want to solve for y, I can multiply the r to the other side, so y is r sine of theta, and x would be r cosine of theta. And this would be exactly how we will be able to convert a coordinate that is in polar form to the x and y values that will represent the rectangular coordinate. So the equivalent rectangular coordinate will be simply plugging in 4 for radius and pi over 4 for theta, and then we can find the x and y values, and they will be our x coordinates for our in our rectangular coordinate system. So cosine of pi over 4 will be root 2 over 2. Sine of pi over 4 is root 2 over 2. Multiplied by 4. 4 over 2 is 2. So 2 root 2, 2 root 2 would be our ordered pair if this were a rectangular coordinate system. So why use polar coordinates? Graphs that aren't functions in rectangular form can still be functions in the polar form. Some of these curves can be quite elaborate and are more easily expressed as polar rather than rectangular equations, and the following explorations will demonstrate that. So again, polar forms are useful for equations with a lot of curves, and also for these non-functions. Okay, these graphs that are non-functions. Okay, so let's look at some of these graphs that we're going to have to be familiar with. Example 2 says put these in your graphing calculator. So you can go to polar form, polar mode, and radian mode in your graphing calculator. And when you do that, instead of y1 and y2, you're going to get r1 and r2. So in your calculator, you can select, make sure you're in radian mode and make sure that you're in polar form. And when you go to y equals, then you're going to see r sub 1, r sub 2, which will begin to resemble these polar equations that you're going to plug in. All right, so we're going to do some of these without the calculator, so that we can kind of begin to see how these are created, how these equations, these graphs are created. A good place to start is always 0. So if I plug 0 in for theta, cosine of theta will be 1. So 0, 1. So 0, 1 is just going to be the ordered pair on the on the polar axis. Okay, I'm just going to pick some easy values here. Pi over 2, cosine of pi over 2 is 0. So that means we're going to start here, and it's going to curve back to 0 at this pi over 2 line. Okay, and then finally, at pi, So moving on to pi, we're going to be along this line, but then if I plug in pi, I'll get cosine of pi, which is -1. So that will bring me back to this point. So, and then that will create a circle that moves in a counterclockwise rotation. And we can complete one rotation from 0 to pi. Okay, so anything in this form, even with the coefficient, will indicate these circles. So r equals 3 cosine of theta. If I plug in 0, I'll get cosine of 0, which is 1. 1 times 3 is 3, so I start off at 3. So these numbers here will represent the diameter of your circle. So here there's a leading coefficient of 1, so you see the diameter of 1 for the circle. You see there's a 3 here, so that 3 represents the diameter of a circle. Okay. And your cosine graph will always be symmetrical about the x-axis. And if I do pi over 2, I get 0. If I plug in pi, I get -3, so that will bring me back to my original point. So this will be r is equal to 3 cosine of theta, and this completes the rotation in from 0 to pi. Now, if I do a -3 cosine of theta, then that will flip this to the other side of the y-axis, but it will still move in a counterclockwise direction, and it will still complete one rotation from 0 to pi. Now, if we have r is equal to 4 sine of theta, 4 indicates the diameter of our circle, but now, rather than being symmetrical about the x-axis for cosine, sine will be symmetrical about, we'll have a vertical symmetry about the y-axis. So let's go through the points here. 0, 0. If I plug in pi over 2, I get 4. So after we move along the curve to pi over 2 degree, pi over 2 measurement, then we're going to get a value of 4. So that'll bring me up to that point. And then finally, pi will bring me back down to 0. So it'll create a circle along the positive y-axis. And if we do a -4 sine of theta, then that will move us to the other side of the x-axis, and will be a mirror image on the other side of the x-axis. Okay. So what do we notice about these above graphs? The diameter of our circle will match the coefficients, right? Diameter is 1, diameter is 3, diameter of the circle is 4 units. This will trace out in the counterclockwise direction, and it will complete one rotation from 0 to pi. Okay. Cosine has symmetry about the x-axis, and the sine graph has symmetry about the y-axis.